Swayam Prabha. Digital India. Educated India.
Welcome back to acids and bases. We've done a lot of acids and bases in general chemistry. This is just extending all of those concepts with absolutely no change to the realm of organic chemistry. So this is basically acids and bases in organic chemistry. But the chemistry itself is the same. It's just the molecules that we're going to look at are different. Since we've already done hydrochloric acid and sodium hydroxide for like a whole year, let's look at something new, shall we? All right, so we talked about 3 types of acids, definitions, acid-base definitions, and you know them all: Arrhenius, Bronsted, and Bronsted is what we use here mostly, but I'm just throwing that in just for historical reasons. And Lewis, the same Lewis. All right, Arrhenius define acids as proton donors, define bases as hydroxyl donors. So H plus donors. And the side on the right would be for bases. So when I write things here, it'll be bases. Let's go. So Arrhenius said acids are H plus donors. And so we, like hydrochloric acid spits out a hydrogen. But we have different molecules here for organic. Hydrochloric, hydrogen, chlorine. There's no carbon, hydrogen there. So let's go find something that's got hydrogen and carbon, and that makes an acid. This is an oxyacid, which is the most common organic acid, which is a carboxylic acid. And you can have hydrogen, carbon, anything you want there, that's organic. So this can spit out a proton. So that means it's going to, these hydrogens are going to be given to the electronegative oxygen, and it's going to go as an H plus. So then your O is going to have 3 lone pairs, which makes it a negative, and your H is going to become a positive. This is only going to happen typically when you have water, neutral water. H2O wants to grab that proton, and then it will become H3O. 2O plus another positive. And then when we talk about acids and bases, what we mean by acids is basically hydronium, which is this. A proton is not going to be running around all by itself. It's going to be tagged to a water molecule, and it's going to swim around like it jumped on top of a water. So it takes a ride on water, and that's a hydronium. It doesn't like go by itself because that's just nothing but a proton. So here, the bases are going to be things that spit out hydroxide. And so example, let's say ammonium hydroxide was our example. So we can talk about, let's say, something like this. And when you have very, very long chains, let's say N is going to be 10, 20, 30. These are things that you find in your fabric softener. They go into your fabric softener, and if it's, let's say, a chloride, and then they weave in, make it nice and soft, or it's in your dishwashing liquid. So these are the bases, soft bases that you have there. Here, I mean, if you put this in water, water is just going to aquate it. So this might be like a solid. If you put it in water, water is just going to aquate it. It's going to become aqueous. So that's just NH3 plus aqueous. And then these are going to be hydroxide aqueous. I mean, this is pretty much what we had in mind when Arrhenius was talking about sodium hydroxide. Let's talk about Bronsted here, where you have an acid that is here too. The definition is the same. Acids are proton donors. Bases are proton acceptors. Here, H plus donor, OH minus donor. Forgot to write that down. So H plus donor, what is it going to look like? I mean, there's so many of them. I'm just going to draw one of them. Like, we can take that, and if you don't have a hydroxyl, and let's say you came with a chloride or something, it's an ammonium. So it can be just like NH4 plus. It's some X minus, some anion, sulfate, even whatever. So this is going to give up its electrons to the nitrogen. Things like to be neutral in organic world because your solvents are typically neutral. So we love neutral things. So it always favors going to the neutral. And let's say you have water here. Water will accept that and become a hydronium. Okay, and that's your acid. When we say acid, this is the guy we mean. This is the guy that goes and changes the pH paper red or turns those indicators to different colors. It's just this guy. This is what we mean by acids. So here's your acid. And when you deprotonate an acid, it becomes, let's say this is acid 1, it becomes a conjugate base of that acid. And here where acids react with bases. So let's say this is your base. So then when it picks up a proton, it becomes the conjugate acid of that. So I'll put 2 here. So then that's your definition for Bronsted. H plus donor, this is your acid. Goes over here. On this side, this is going to be donating the proton to go in the reverse direction. Proton acceptors. So to accept a proton, you got to have extra electrons because protons are positive. So when you have extra electrons, then you can be a proton acceptor. So typically Bronsted bases would have lone pairs in them, oxygen, nitrogen, all of these. And then you can add to this a, say, a hydrochloric acid or some acid here. So you always draw arrows from electrons to electron holes, protons which have no electrons, which are just basically nothing but a proton. So always your arrows have to go in that direction. So here is your oxygen now, lost a lone pair, and the lone pair actually became a bond, and there is your hydrogen. And so this is going to be 6 for oxygen, but it's only got 1, 2, 3, 4, 5. 6 minus 5 is plus 1, so that's a positive charge here. And the counter ion is a chloride. Here's an example. There are millions of examples for proton acceptors. You can think of this as a nitrogen and doing the same thing. Let's look at Lewis' definition. What did Lewis base it on? Lewis didn't talk about protons, he talked about electrons. I mean, pretty much saying the same thing, but in a different language. Electron acceptors, because you can see how something that has a positive charge can accept electrons, are acid. Acids. And electron donors are bases. So this is your Lewis definition. So electron acceptors, what can accept an electron? It's got to have an empty orbital. It's got to have space for electrons to flow in, right? So things that have unfulfilled octets, empty orbitals like positive charges, they're all fair game to be labeled a Lewis acid. A typical example would be a lot of our catalysts are Lewis acids like aluminum chloride, boron trifluoride. Why? 3 sigma bonds are going to give you just 6 electrons. It doesn't have 8. So it's going to grab electrons from somebody to make it an 8. So let's say you take this and then you can have anything going and making a bond with that. So let's say you have a lone pair here that can go in, and always electrons to hole. So you have aluminum, and then you can put a bond to this oxygen. So oxygen just lost a lone pair, it's positive. And then aluminum would be negative. then the reaction, all of these reactions are also electroneutral. Plus total on one side, plus on this side, same. Over here, zero charge, plus minus zero. So make sure your atoms are balanced and your charges are balanced. You can do the same thing with boron and so on, group 3 elements. Or you can talk about something that doesn't have electrons, even a proton. Let's say you have carbon positive. That means carbon that doesn't have its octet filled. This can also react with something that has got oxygen or nitrogen, something that's got excess electrons or lone pair electrons. So this can go in and attack that. And so you can see, well, now you have your oxygen lose a lone pair, and so therefore it's going to have a positive, electroneutral overall. So you can have a lot of different types of reactions. Let's look at, let's say we have a very simple electron acceptor, which means it's got to have either a positive charge, empty orbital pretty much. So here you can put any kind of electron pair. You can put lone pairs. You can even put pi bonds here. So let's say you have a pi bond here like this. The pi bond is a little bit loosely held compared to the sigma, which is in the internuclear axis, and you can't really move it. Pi bonds are, like electron blobs above and below that sigma bond, so they're a little bit more flexible and mobile, and they can go over and attack that H+. And so here you can see that this hydrogen is going to tag along here. And because you took electrons from here, now this is electron deficient, and you'll have a plus. Okay, so all of these are examples of Lewis acids that are accepting electrons. Now, there's another name for Lewis acids. They're called electrophiles. Phile means love, so they love electrons. So these are electrophiles. So Lewis acids are also called electrophiles. And these are lone pairs, and these are electron donors. They love a nucleus. They're called nucleophiles. Electrophiles and nucleophiles always go together in reactions. Always draw the arrow going from the nucleophile to the electrophile. Always. And well, this is pretty much the same here. We can draw a few more examples if you'd like of electrophiles and nucleophiles. So let's say you have electron donor, nitrogen here. It's got a lone pair, and it donates electrons that will make the Lewis base. So then you need an acid for that. An acid can be anything, a positive charge. Let's say you have a positive charge like this. Then you can take your lone pair and pour it into that empty p orbital and make a bond. And so you lost that lone pair, so you're going to have a positive, and here is going to be a electroneutral reaction. It's an addition. We can think about, let's say, pi bonds. In this case, let's say we have a benzene, and you have, let's say, a electrophile like this. The benzene electrons, because this is so strong, can go right over here and knock this off. So here is an example of a pi bond, which is a electron donor that acts as a Lewis base. And so you pull the electrons off of here, so you have a plus, then you'll have a nitrogen. And here again, you have 4 bonds to nitrogen, which makes it a positive. So there are so many examples out there for these types of reactions. For example, you can have a pi bond, and you can put in, let's say, a really reactive bromine. Doesn't have an octet. It's going to rip off that pi bond in no time and put it right over there. So over here, you can see these are all electron donors. They love positives. So they love nuclei, which is positive. So this will be called nucleophiles. So in this case, bases are nucleophiles. And these are positive. They're greedy for electrons. These are electrophiles. When they break one thing, those are addition products here, ducks. So here, your nucleophile seeks electrophile. There you go. So you can see Lewis acids and Lewis bases are good definitions also for electrophiles and nucleophiles. Pretty much the rest of your organic chemistry would be reactions between electrophiles and nucleophiles. That's why this is an important topic. How do we know whether this is going to act as an acid or a base? How do we know? Well, we have what you call an equilibrium whenever you have an acid-base reaction. Even though I've drawn these arrows, they can go back and forth. So we can find out which direction the reaction is going to go. So over here, is this going to go in this direction, or is it going to go in this direction? If it's going to go in this direction, obviously this is going to be the one that's dissociating, stronger acid. If it is going to go more in this direction, obviously this is the one that has to dissociate and react with this. So this will be the stronger acid. How do we know then? Can we just look at it and figure out? There's another way that's actually a lot more accurate, which is looking at pKa values. What does that mean? What's a pKa? Just the same stuff you learned in Gen Chem, guys. It is just an equilibrium constant, negative log of Ka. So if you take an acid, here is your acid-base equilibrium. So if you take HA, and let's say it goes over here with water, H is going to split into H plus and A minus. The H plus is going to kind of piggyback ride on this water. So basically this picks up and goes on has a piggyback ride on that. So that's called the hydronium. That's really an acid. So now this H3O plus concentration goes up. We're going to put our finger in it. Ouch! It's acidic. It's corrosive. We're only measuring this molecule here really when we are talking about acidity. And so the more it goes over here, the more acidic this is going to be, the solution is going to be. So K equilibrium here is nothing but, in this case, because it's an acid, we'll call it a Ka. So Ka for this acid-base equilibrium is going to be H3O plus A minus over HA. So the higher the H3O plus, the higher the K value. So Ka goes up, acidity goes up. Ka is proportional to H3O plus concentration. It's proportional to the acidity, acid strength. I know in Gen Chem you talked a lot about pH. Is it the same thing? Not at all. pH really measures what's the concentration. It means how much water do you have and how much acid do you have. So that's the measure of pH. pH can change. For example, if you take HCl, pH can be less than 0 to close to, like 6. So because the amount of water changes when you dilute it. and so the pH will go up. Ka is not going to change for HCl just by the way we define it. It's a ratio that's going to be pretty much constant. If at all it changes, it's going to be because of temperature, not because of the concentration. So Ka is just a ratio. So when you have a certain acid that with a certain strength, it will give a certain amount of H3O plus and A minus. Those amounts will be constant at that temperature. So the ratio will be constant at that temperature. You can't really change it by putting more acid, then you're also going to get more of this, so the ratio will be the same. So therefore, pH and Ka are not the same thing, pKa and pH are not the same thing. Something that's a little easier to measure is pKa, and pKa is equal to the negative log of Ka. So therefore, chemists always think like in opposite direction. H3O plus goes up, pKa goes down. So acid amount goes up, pKa goes down. So the lower the pKa, higher the acidity. But of course, Ka will go up as we have put it over here. So pKa for acids is a huge range, all the way from something like wood or something like gasoline, which is like completely, totally neutral, to something like sulfuric acid that can kind of chew away your hand if you put a hand in it. So like we have organic molecules in that range, all the way from completely neutral to extremely acidic. Okay, and then also, we will talk about the bases also. So pKa can have a huge range from 50 to about -11. That's the range we're talking about. That's huge. pKa 50 is Ka 10 to the -50. pKa -11 is Ka 10 to the 11. So like a billion times to like 1/trillionth of a trillionth of a trillionth. That's how little this is going to dissociate. So Ka basically measures the dissociation of the acid. It's a dissociation constant. Down here, I have this huge scale here. What is this all about? We're going to try to see all of the things out there in nature and compare their acid strength. Some things like a sulfuric acid, iodic acid, I mean, these things, even if you get a drop on your hand, it's going to like go through your hand. It's that acidic. Whereas you can take things that are so neutral, there's nothing that's going to happen to them. Like your butter or your oils, or just gasoline or things like that. Unless you light a match to it, it's going to be there underground for millions of years. They're not an acid or a base, they're just plain neutral. But even those, we have a scale. How much hydrogen can it spit out? For example, let's take something like ethane, which is coming through your gas pipe, like 20% of it's ethane, and about 80% methane. So those are just hydrocarbons. So take off a hydrogen. So when you go from here to here, all we're doing is taking off minus H plus. So you're going from an acid to the conjugate base for all of them. So this acid and conjugate base is always one proton less. Conjugate acid is one proton more. If you get more than one, it's not a conjugate. So here's CH3, CH2, and then we're left with the positive, so the negative is here. Now that's like the most neutral substance out there, or the least acidic stuff out there. There's nothing really less acidic than that. pK is like 50, 60 and so on, in that range, depending on whether it's primary, secondary, tertiary and so on. Now, if you got an alkene instead, put a double bond, now that gives off hydrogens a little bit more readily compared to this, but still it's neutral. Okay, so here minus H plus goes over here, acid and conjugate base. That's pKa 44. Okay, that means this equilibrium is almost entirely here. Ka is going to be 10 to the minus 44. Here Ka is 10 to the minus 50. You know how small that is, 0.0, 49 zeros and a 1. All right, so that's teeny amount of H plus that comes out, which is like nothing. What's 38? Well, you can take ammonium and that's going to be 38. So if you take, let's say, ammonia and take off this hydrogen, ammonia, and take off that hydrogen, and let's say you have 2 lone pairs, which makes it a negative. That's 38. That's going to be the Ka for that equilibrium is pretty much all entirely here. Just like here. All of these are almost entirely in this direction. Ka here is 10 to the minus 38. 25, what's 25? Well, believe it or not, that's going to also be a CH, but this CH happens to be more acidic than even an NH. So here you're going to take a C and minus out of this when you take away a proton. And so the Ka is 10 to the minus 25. Now here's a big gap here. There are other molecules, but you're not going to see them. So here, let's say we take a molecule like this. And you might think this is just acetone. Why is this even considered an acid? Well, it's actually way more acidic than, let's say, gasoline. This hydrogen coming off, CH2 minus CH3, that's 19. So you can see, I'm just going down this just to show you here. Talked about resonance, so you can have some resonance here. And so that's why the pH has dropped for this carbon, CH, compared to this carbon. They're both CH2s, but look, this is way more acidic because the anion is stable. Let's talk about 18. What's 18? We're coming to oxygens, OH bonds. Oxygen's electronegative, so you can spit out that hydrogen and become a nice anion. That's tertiary's 18. Now if you go less over here, just primary alcohol, that is going to be, spit out that hydrogen and you have a minus, that's 16. Now over here, this is kind of where the neutral ground is, water. Spits out a proton and you have OH minus. So let's say water is our neutral point. All of these things are less acidic than water because Ka for this is 10 to the minus 15.7. That's a lot more dissociation than 10 to the minus 50. So over here, this is going to be a lot more acidic than any of these guys. Let's see what's going to be even more acidic than water. Nitrogen with a positive charge here. These would want to get rid of this hydrogen to become neutral. So therefore it's more acidic than water. That's about 9 to 10, in that region. 9.9. So over here we have a special kind of alcohol which we call phenol, and phenol going to a phenate ion. Phenol going to a phenate ion is going to be even more dissociating because this has lots of resonance and it's stable. Well, here's RSH. Sulfur is a big atom and it can be fine. It's a big boy, it'll be fine without that hydrogen, it's stable. 9 over here, let's look at this over here. Let's look at this molecule over here. So this is an exception here. We have a carbon-hydrogen bond, and that is actually going to come off a CH and become an anion here. And you might wonder, what's a CH doing here? All the CHs were over here. Why is it even more acidic than water and phenol, which is your toilet bowl cleaner? The reason being, this anion can become conjugated with this carbonyl, and it's spread out over here. And we talked about resonance, more conjugation, more resonance, more stable. So that's kind of pushing it towards this molecule. Ka is 10 to the minus 9. So let's keep going and see 4.8. That's your common acetic acid, which goes to an acetate and spits out a hydrogen. 4.8. You might think acetic acid, it's so acidic. It's still, Ka is still 10 to the minus 4.8. It's still less than 1. Which means most of it is still starting material. So when you drink vinegar, it's only a little bit of protons come off, not all of it. If all of it came out, it's going to just burn down your throat. So that's why we like mild acids for our fruit juices and so on. Getting more and more acidic. Now we're coming to things that have charge, that want to let go of their charge. So here's a pyridinium molecule. And it wants to be neutral pyridine, so obviously it's going to spit out that proton the first chance it gets. And that's 3.4, 10 to the minus 3.4 Ka. Now you're getting into the real acids, negative 1.7. So here's your protonate water. Obviously it's unhappy here and wants to go down and become neutral water, just like in the ocean. So now that's 10 to 1.7. Now it's greater than 1. So here's kind of like a tipping point here where you're now getting into stronger acids, pretty much strong acids. Minus 7 to minus 11, that's all your HCl. That's minus 7, HBr, minus 9, and minus 11 is HI. So the anion is going to be X, which is like chloride minus or bromide minus or iodide minus. And what's more acidic than that? Well, the acid we are all afraid of, sulfuric acid, furic. Can get really furious, burn down the house. So that's your sulfuric acid. It's one of the strongest acids in the lab. So that's minus 9 and minus 11, just going to put it here, HI. Of course, we have superacids and all kinds of acids that are stronger than that, but we don't really use them. Okay, these are the acids that we usually see. There's a lot of acids and bases. Just wanted to give you kind of an introduction on acids. Now, how do you know what's going to react with what? This is important, guys. This is going from weak acid to strong acid. And so therefore, this on this side is going from weak base to strong base. So these are the strong bases. These are the strong acids. Obviously, when they meet, they're going to react instantaneously. So you want to have an acid with a low pKa reacting with a base with a high pKa. Strong base will deprotonate the strong acid in a shot. Now, when you come down here, well, you're still going to get a reaction, but when you cross this, a weak base is not going to pull off a proton from a weak acid here. It's not going to happen here. So you should always have the acid on this side and the base on this side for it to react. You know that pKa or Ka times Kb is a constant. So if Ka goes up, then you know that Kb will go down. So that means basicity will go down. On the contrary, if pKa goes up, then your basicity is also going to go up because you know pKa is opposite of Ka. So pKa increases, then basicity also increases. Kb goes up and basicity increases. That's why when the numbers go up, all the conjugate bases here, these are the strongest bases out there in the world. These are the most strongest on our base scale. It's over here when the pKa is high. pKa is low, these are neutral. Sulfates and chlorides, those are neutral because conjugates of strong acids are neutral. So these are neutral. So pKa can also be used to define base strength. pKa is high, basicity is high, and pKa is low, basicity is low. pKa is high, then acidity is low, pKa is low, acidity is high. That's something to take home here from this video, is the pKa scale is useful for defining acidity and basicity. When we come back, we're going to look at these numbers and predict, is this reaction going this way or this way? Which direction is it? It's easy to do once we have our scale. I'll talk to you soon and let me know if you have any questions. Bye.